I have not set up the due date yet. I mean, it's for the last assignment because I needed to make sure you finish the previous assignment in time. So probably that will be maybe 10 days or 14 days, I don't know. So I think in the next week, I still need to give you some lab instruction. So definitely the due date for the last assignment probably will be 10 days from now, from today. I have not set it yet. Okay, assignment 11, right? I made a mistake. Okay, I given you a pack, assignment 11 pack. So basically, there is a PDF file, the instruction, and also a skeleton of the class you are going to implement. And I have also given you a demo application right here, and also a set of data set. This data set is, again, the format is designed by our lab. But probably if you have a similar data set, you can kind of convert your data set into this kind of format. The format is so clear, I mean, it's self-explanatory. And you pay attention to here. The data set are basically depict from the available benchmark in the internet. So let me show you. Basically, these data sets are small size. It's not large size. So input are usually real number, not an image or not a file continuous data at all. So let me show you. So at least that means once you finish your MLP application, you should try this data set. The first one should be a breast cancer data set. It's a famous data set shared by the Wisconsin University Hospital. So it's a breast cancer data set. It's small. So I kind of, in our lab, we kind of prepare the data set as a standard format. So again, this data set is written in text format. So the first line tells you the information about the number of data in this data set. So basically, in the first line that you will get line number. The first number is the instance number, training instance. So that means in this file there are 698 records. And the second numerical value is the number input. So number input, as you can see, the first 9 data are input data. So number input field, data field should be 9. And the last, the third number is the output number. So output number is right here. So that means this is your input, this is your target value. Okay, so that will be the one instance of training data. So we have input value here, and we expect if your neural network is good, your MLP is good, then it will predict the output value should be the 1 and 0. So the output value is 2-dimensional. But as you can see, the output so-called one-hot vector by default is vector because this data set is a kind of classification problem. So that means we have 698 data instances. Basically, these data are classified into 2 groups because it's a cancer, right? It's a breast cancer medical data. So you can presumably suppose that each instance should be a patient. The medical indexes or certain kind of measurement index. And in fact, you can check about the physical meanings of each data. I mean, later I will show you the original of this data set. It's come out from, it's depicted from UC Urban. There is a so-called data set library there. So we picked it up there. And I don't think, do we have comment information here? Let me check. yeah, we also include that information. So detailed information about this data set is appendix in the real parts of this data set file. So what you need is that you need to read in this 698 data rec from the second line. So the second index, the second number is the input dimension. Third one is the output dimension. And the last one is that if this input is actually two-dimensional data, then the number, the first number, because if the input is a two-dimensional variable, right? So we will have another information indicated that the width of this two-dimensional data. So this data format can just take care about one-dimensional input or two-dimensional input. So if it is two-dimensional input, then the dimension of the first, the length of the first dimension is depicted here. So since right now it's a one-dimensional array, so actually 9 is not really participating in our data construction. But again, you need to read that in. So once you read it, then you know the input dimension is 9, and the width of a two-dimensional input is 9. So actually, that is a one-dimensional input. So you need to read that. So in comparison with the two-dimensional data, so let me check about this one. Letter recognition. Okay, letter, we know it should be letter recognition. So, excuse me, 16. No, not this one. A to Z, probably this one. Okay. For this, for example, this data set is the input is two-dimensional. So as you can see, there are just 26 training data, and then the input dimension is 81, right? 81. So as you can see, the entries are all 0 and 1. So for each instance, the first 81 data are input data, and output data is 26. So 26 is 1 half. So either way, just have one instance is 1. So basically, that stands for A, B, C, D, the character, English character letter from A to Z in that case. So in this case, the input is 9 by 9. So totally there are 81 01 value there. So for example, once you read in this input data set, then since the first number is not exactly equal to the second number, right? So you know that it is two-dimensional data set. And usually, once you take the module operation, so that should be evenly divided by 9. So in that case, you know 81 divided by 9. So you will know that should be a 9 by 9 input data set. Okay. All right. So let's back to this file again. So input number is 9. Output number is 2. And the width, so the input is 9. So, and as you can see, so almost this certain kind of index, integer index, right? So if you know the medical meaning about each medical data, so you can check the explanation in the real part. So after 689 data, we put texture right here. So this data set is shared by the I don't know exactly the source, probably from a paper or anyway. The data is basically generated from the Wisconsin hospital. So you talk about, so currently literature, several literature has used that data set for their research. So you have a certain kind of literature review here. You can check that out. And sources right here, okay? Physician, right? So Williams Hopkins, University of Wisconsin Hospital, Madison, Wisconsin, USA. So past usage, then they have certain kind of record about the usage of this data set in the literature. Okay, so 999. I think probably one data set has certain kind of data missing. So currently we just correct 698. And then this is the physical minutes for that medical measurement right here. So 1, 2, as you can see, these are the 9 input value. So the first one has been truncated anyway. So right now we have 5. We have been using the 9 medical indexes for input right here. The scale starts from 1 up to 10. So in our format, we have truncated this user-based information, probably patient ID, like that. It's irrelevant with our domain knowledge, so we just leave it out. So the input is 9 medical index right here. And the last one, because we just has class 2 for vision and 4 for malignant. So in that case, we transform that into 0 and 1 for easier identification. All right. So anyway, we have converted the data set into this kind of format. So 0, 1, 1, 0. So basically, that is a classification problem. So make sure you do run this example because you can make some preliminary checking about your code to see if you have a good and correctness after training on this data set. Another one should be the iris.cal. Iris is a flower, right? So it's a botanical data set. So we have 150 instances. Input number is 4, output 3. So this is a data set containing 3 different kind of iris flower. So as you can see, 1, 0. So some data set might have organized their training instance in a certain way. So in that case, because for the first parts, the iris belong to the first group, right? So 1, 0, 1, 0, 1, 0. And the middle edge should be 0, 1, 0, the second group, and the third class is there. So similarly, you can have the textual explanation about this data set right here. So basically, it's botanic. They kind of measure the flower, the petal length, petal width, and sepal length and the sepal width in order to classify that iris flower into a certain group. So the result shows these 3 kinds: iris, setosa, and versicolor, and virginica. So there are 3 kinds of flower needed to be classified. So later on, if you pick up a new iris flower, and by measuring the sepal length, width, and the petal length and width, the expert system will give you a final class for that newly obtained sample. Right. So okay. So if you build up a neural network that can be the breast cancer expert, and probably might be an iris flower expert system too. So the third one you should look into should be the why that care. So this why data set, again, they have three categories for this classification. Red wine, grape wine classification there. So totally there are 177 instances. Input dimension, as you can see, is a real number. So there are 12 input there. Okay, so similarly, you can see some exploration there. All right, so again, you can find a lot of small size data set from the internet. And I think the famous one I have showed it in the slide, right? So the famous data set is here. UC is UC Urban. So you type UCI, you have the machine learning repository there. So they keep updating the dataset contributed from all over the world. So you can see a bunch of irises right here, right? Why? So if you look into the iris flower, so detailed explanation will be given right here. So dataset characteristic multivariate. They kind of classified this dataset using certain kind of attribute. So total number 150. Area is nature life, real number for source, right? Source. Dataset information attribute. So paper literature review, those literature using that dataset to do the study. Okay, so information is right there. So again, you can pick up and you can download any kind of dataset that interests you from UC Irvine. Okay, iris Y. Let me check. So probably we can type. Oops. That's another way. Okay, breast cancer dataset. So totally they show 500. Oh, okay. I think they have trimmed that dataset into 569. Donated. Anyway, that is a source you can pick up. You can download all kinds of dataset contributed by the world. There. All right, so our mission is that we try to build a multi-layer processor, and then the user specify the architecture of the neural network they like. So probably the user might just specify, oh, I want just one hidden layer, or maybe two hidden layers, three hidden neural network, hidden layer, and then user need to spread the number of neurons in each layer there. And there's no any way, because once the user read in the data set, the input dimension is fixed, right? And output dimension also fixed. So in that case, the number of input neuron and the number of output neuron is not modifiable. It depends, the number depend on the input data file. So let me run the sample application, demo application here. So again, I mean, in the assignment pack, I gave you this transformed data set. So that will be much easier for you to read in and store the training data set in your array, and then do the neural network training. And after that, calculate the correctness, right? So that is the mission for this assignment. So let me show you this demo application, backpropagation multi-layer processor. So first, user need to read in data set. So the extension is .cal file. So we can do here, specify the path. So let me just pick it up, breast cancer, Wisconsin. So once we read in, right, so we know right now the first neuron layer should be the input layer. So input neuron number is 9, so it's fixed. And since it's a classification problem, so output neuron is 2, just 2 cases, right, 2 class. So the parameter can be specified by the user for the architecture of this MLP is just number layer, hidden layer. So by default, hidden layer number is 1. And by default, the neuron is right here, 4. So if you user like to change the number of neuron in the first layer, so user can click on this user interface to change that. So that is 7. And if you use want to set up a so-called multi-layer processor, so he user might wish to add another hidden layer, 2, 3. It's totally up to the user. So right now, this means the zeroth layer, first layer, second layer, third layer, right? So probably use we'll like to change that a little bit, and probably use shrink it. Fine. I mean that's just a user interface interaction. So you just let the user arbitrarily set up. So right now, user asks for 2 hidden layers. The first hidden layer neural number is 5 and 3. So after that, user will click on the reset, right? And let us see what kind of parameter can be set up, by the user. Epoch limit. It's similar to our iteration limit, right? So epoch limit. Initial eta, that means the starting learning rate, eta, starting learning rate. And then once epoch is finished, then the current eta value will be updated by timing it, multiply it by this learning rate. So learning rate is usually very high, it's close to 0.1. So we need to gradually reduce the eta value, right? So eta is actually kind of like a step size. I mean, if you are studying the hard computing, for optimization algorithm, usually need a special step size in order to move your current solution toward the optimal. So, which is similar to the hard computing. So eta is a learning rate. You can regard that as a stepping size. So after one epoch training, we will update the eta by timing, by multiply the current eta with this learning rate. So learning rate is set up to regulate the decrease, the step size decrease tendency there. So if you implement the momentum, right? If you look into the study, because scholars find that the training is not efficiency, so they introduce a momentum factor there, try to keep the modification or the weight in a unified direction. So in that case, if you activate this momentum stuff, then this momentum factor will be used. And after each epoch training, your multi-layer processor shuffle the trained data. If it is true, then you need to shuffle the training order of the training data set. Just training data set, okay? Don't bother about the testing data there. And the most important factor is right here, training ratio. So right now, we kind of dealing with our data set, try to separate that training data set into 2 parts. The first part, so right here, just if very probably, for example, 0.7. So that means 70% will be used for training. So we keep another 30% for testing later. So we are not going to do so-called verification. So if you take some so-called AI courses, then during AI training, usually not just training data, so probably user might allocate certain kind of training data to serve as verification usage. So we are not going to deal with any verification. So we simply divided our data set into 2 groups. One, the first group, usually larger than the amount is over half of the original training instances. So 0.7 is a fair, or probably you would like to set it 0.28, it's fine. So that means 80% of the data will serve as the training data set, training data instances, and 20% will be used later for testing. Okay, so that is the division of your data. So users set up this kind of information, then again, you see there's a reset button there. So once user change this attribute, then you need to hit the reset. So that means we will reallocate memory, right? So probably user change line, current change into 1. So then in that case, 1.5, right? So after we reset, we will have graphics represent the current neural network. As you can see, the input is not modified by the user, right? So once the user reading this data set, I don't think we have information about the data set. So input is 2, 4, 6, 8, 9. 9 input to classify them. And we always has a dummy neuron there. Formulation-wise, we treat the so-called bias, the parameter bias, as a weight, as a normal weight. So in that case, we will expand our model a little bit with an actual neuron, but the value is not modifiable. The value is always equal 1.0. So in order to get a good formulation about the forward computation, so check the slide derivation there. All right, so this is the neuron. So probably user might change his mind. Probably set up, well, okay, I like to have 2 hidden layer. First hidden layer, the neuron is 4. Second neuron is 3. Fine. So it's totally up to the user. So in that case, run reset again. So as you can see, once user click on the reset, you need to reallocate memory, right? Because right now we have different number of layers, and we definitely have different number of weight. You need to initialize your weight. So it's randomly assigned. So if I click reset again, as you can see, the weight has been initially assigned with a random number. I think that value should be between 1.0 and minus 1.0. Alright, after that, we train an epoch, which is similar to wrong one iteration, right? So again, I mean, since they are soft computing techniques, so they share common philosophy about solving a problem, right? So train an epoch. So we need to monitor the progress about the error. So once we hit the train epoch, all the training data has been fed into the neuron. And then for each instance, once we get the error will be propagated back layer by layer in order to get a gradient with respect to the weight. So each weight, so once we calculate the error propagation back to the first error, after that, we update our weight, right? So optimization procedure is actually carried out once we feed in one instance and then the error propagate back. In that case, we update our weight, try to move the current weight into the one which will generate less error. So that is the optimization procedure. By finding the duration or the weight change, right, to update the weight value in order to minimize the error. So actually, the training of neural network is actually a procedure of optimization in order to reduce the error. All right, so one epoch. So note that one epoch you need to feed in sequentially for each training data set. So basically, the weight has been updated many times there. So after that, we will calculate. So for each epoch, we correct the error, total error, right? So once we complete the error, so we calculate the root mean square error right there, and then reported it out. So first epoch, second epoch, then run another epoch. So all the data set will be forward again and backward compute the error again, update the weight for each instance. So right now we shuffle each epoch train, right? So once we finish an epoch, we need to shuffle the orders of the training data set. So that means the first data will no longer be fed in, I mean, in the very beginning in the next epoch. So make sure you do implement this kind of option. Okay, so train epoch, another epoch, right? Another epoch. You might see why. In many user algorithm, what we keep is so far the best solution. So there should be no way that so far the best objective value raise up, right? But it's a root mean square error. So it's not guaranteed that it's monotonic decrease. All right, probably, I mean, at the end, you will raise up, keep increasing too. So that shouldn't happen. That means you might have overfitting cases raise up there. So train epoch. So stopping conditions right here, epoch limit 500 epoch. So we just let it run to the end. So we need to monitor the error, mean square error. Right? So since the whole procedure is an optimization of procedure, right? So probably your solution is stuck on some local optima. So in that case, even though you train more epoch, but the error is not reducing anymore. So probably you hit the local optima. So once the limit of epoch reached, then we will use the testing data, try to compute the result and compare with the target value. So as you can see, right now there is an instance calculation right here. So at the end of the upper neuron, the value is 0.99. You are not going to expect that it will be exactly 1.0 and that should be exactly 0.0, right? So if you add test instances is fed into this neuron and do the full computation, and after this case, so we find if this is bigger, then this instance is classified into group 1. This is group 0. And compare with the D0 and D1, the target value. If it is larger, and then the target value, this one is larger, then we will say that, okay, this classification, this testing is correct. So we count, we set up a so-called confusing table right here, So that means the class 1, the training data right now is 140. Totally, the number of testing data is 140. And 90 of them are belong to the group 0. And we have classified, after the training, we have classified that instance into the 0 school. So it's correct. 0 schools classified into class 0. So 90 is correct. And 45 belong to group 1 and has been classified by this neuron into group 1. So it's correct. But of diagonal terms or diagonalism are the count or incorrect classified, right? So 3 of them actually belong to class 0. But once we fit it into our current neural network, the result is that it has been classified into the class 1. So it's wrongly classified. So number is 3. Similarly, this the wrong classification is 2. So totally we will compute this correctness value. So it's simple, just the sums of diagonal terms divided by the total number. So right now we have reached the correctness value 0.96. It's quite high, right? We have set up 2 layers and then all right, so that is one case. So again, as I say, the neural network training is actually an optimization operation, right? So in order to minimize overhead, so we can treat that training as an optimization problem and use our GS solver, use our PSS solver to evolve the initial weight into a set of weight that would minimize the total error. So as you can see, this is the training by the neural network, which use the greater distance, the hard computing weight to minimize to train the neural network. Actually, the so-called training is actually try to find a set of weight that best fit the input and output relationship. That's it. So again, if we use GA, try to solve the problem. So we create a GA solver. So it will turn out to be a real number optimization problem, right? Variable as well, variable are those weight. So the weight will have a lower minimum and upper limit. So usually we set it to probably -10 up to 10. So we have real number. And how many variable right here? In this neural network, we are total there are 63. So what is the objective function? Well, you need to look through all the training data and then compute the error. So after full computation, we will get a final neuron value, right? So we divide it, we subtract it out with the target value and take the absolute value, take the square, and add it up. And after all the training data set has been fit into them, we compute the least square error. So least square is our optimization, is our objective function. Try to minimize that. So it's an automation problem. It's automation. Remember that it's an automation problem. So right now we are population size 40. Okay, so we reset, run one iteration. So we simply show the current objective value, current mean square error. So let us run to the end. So the termination condition is that 200 iteration. We employ 40 chromosomes to evolve this solution. So run to the end. So after the end, similarly, we will construct the confusion table and calculate the accuracy. So as you can see, well, it's close, right? 0.97. It's a little bit better than the neural network. And you might wish to check about the CPU time used. Fine, that's all. Or you can always use different kind of methods to try to train a neural network. Anyway, so since continuous GA can solve this problem, right? So similarly, we have PSO. Right, PSO. Again, so we create a PSO solver. So the same condition, right? Almost the same condition. 200 iteration limit and 40 party will be employed. So factor, combination factor, reset, train one iteration, run to end. Well, if you use implement PSO and GA correctly, you should have similar behavior. PSO is poor, in dealing with high dimension optimization problem. If the dimension is 2, it's okay. For both GA, PSO can solve the global demand. But GA again is popular, is kind of powerful for high dimension problem. But right now it's a high dimension optimization problem. For particle swarm optimization, it's poor. We're not going to get a good result for it. I don't know, I'm not sure for exactly what's going on. Probably my PSO problem here. I don't know. But you can always use the tool you develop to train a neural network. Right? You are not going to just use a hard computing way to do that. But totally, the neural network approach to establish expression is a soft computing technology. Right? All right, so that is well. So probably user might I just want to, because the data set we are dealing with a small data set. So usually we are not going to set up a so-called deep learning neural network. It's useless. It's not necessary at all. If your input dimension is less than 100, definitely you should use a multi-layer processor will be enough. Currently AI attract a lot of interest, right? But because the current AI is trying to their input information is large. For example, an image, right? A picture. So a picture might, if the pixel, the resolution is 1,000 by 500, and definitely the input dimension is 500,000. So it is not possible to set up multi-layer processor to do the training. So usually you have to use different architecture or neural network to construct the front part. But for deep learning AI neural network, usually the real parts are NLP. So they kind of try to reduce the input information into a size that affordable by multi-layer processor. So usually multi-layer processor, the structure is usually attached to the real end or a deep learning neural network there. All right, so suppose you use a 20 different kind of architecture within neural network. So as you can see, the first model we use up 63 variables, 63 weights to represent this knowledge of the breast cancer, right? Right. So it's enough, right? We can almost get 97% correctness. But right now, if you just use 4 neuron and 1 hidden layer. So once we reset, and if you look into GA, we just use 5. Okay, this architecture take up 50 weight. So again, reset, and then we train to end. So after the end of training, we classify the testing, set up this confusion table. So currently, it's good, 99%. Okay, probably we just reduce a little bit into 3. Reset it, and if we stage it. So right now we just use 38 weight to represent this knowledge of the breast cancer diagnosis, right? So the whole idea is that we try to set up an expert system. We don't know the knowledge between input and output. And we try to set up a neural network in order to construct a formula, try to get the function, that regulate the input and output. So if we can find that equation correctness, and correctness is 100%, then definitely you get the solution, correct global solution, right? So right now, the number with reduced to 38. So similarly, we still can ask the multi-layer to train the data set for us. Again, correctness is almost 99%. So once you construct your application, remember that practice the execution with different kind of parameters to learn the insight about the neural network. So it is not guaranteed that you use more weight will get better correctness. It's not necessary, all right? But again, if you just use 2 neuron, right? So 1 hidden layer, 2 neuron. All right, so once I reset, so right now, number of variable turned out to be 26. So right now we use these 26 weight to represent the knowledge of the breast cancer. You can regard it in this case. So let us see what kind of training result. The training conditions are all the same, right? So as you can see, the correctness is still 96%. So that means this data set is clear. I mean, it's clean somehow like that. So probably let us, excuse me, this is the result from GA, right? Sorry about that. So let us go back to the neural network. So training to end. Correctness is a little bit inferior, right? 94%. Okay, so that is for the Wisconsin breast cancer data set. So make sure you test this data set because it's a traditional, it's a well-known benchmark problem there. So another one is the iris, right? Iris right here. Iris cat. So iris. So again, we still use the same structure, 1, 2, right? We reset it. So number of variables, just 19. So we start with these generalized data rule to train our neural, train to end. This data set contains 3 classes, right? So the confusion matrix should be 3 by 3, right now. So as you can see, the correctness is still 94% high. It's not bad, right? We just set up 1 hidden layer with 2 neurons there. So if we employ a GA to get the value of the weight, again, 92% correctness. Right? PSO, let us give it a chance again. I don't know. Probably my PSO is problem. I don't know. You can apply your PSO to solve this problem too. All right. So it's inferior. Okay, so this is another data set, famous data set iris here. Another one should be y.cal. So similarly, we set it. All right. So train to end. Ruby Square is a good index for the training result, right? So because it keep reducing, it's a Ruby Square has its absolute scale. So once it's the final value is less than 0.1, definitely you should have a very good correctness. So currently is 90.97%. How about the GA? So right now we have 35 because we have 3 groups, so number of variables is a little bit higher before. So currently it's 98%. All right, so that is the assignment we like to build up. So the most important thing is that we need to build up the multi-layer perception to train a data set and then serve as an expert system for this area, for this data set. Okay, that is the idea. So, is there any question about the current exploration of this new assignment? So in the next class, I will show you probably how to read in that, how to prepare the data structure, and then if I have time, we'll talk about how to do the graphics job, I mean, here in your application. All right, so let us take a break, and then we'll continue the labor instruction. Okay. All right, so let us continue. So use the demo app to learn what you should have done in your assignment, okay? Okay, so our application should be able to read in the cat dataset file and then can configure and then based on user specification. So you need to print what kind of functionality should be done something in order to interact with the user. So user might change the property, right? Some property of your multi-layer processor, and also change the configuration. So once user changes the configuration, then once he hit the reset button, what kind of information should be reset? So that including memory relocation and also weight initialization. So you need to carefully print what kind of job, what kind of position should be done in each function there. But basically, you just take a look at the interface button there. So user can change that. So basically, user just set up this list. If the list is just one element, that means there's one hidden layer. If there are more than one number in this list, right? So that means more hidden layer will be required. And so once we read in, okay, if we use read in a benchmark file, a data set, that means the MLP has read in certain kind of input information, data information. According to, and probably user will change the fraction, right? Training ratio. Or probably user might, well, never mind, it's a training ratio, just a value, right? So number of training data will be set up there. But once the user click on this button, then all the data should be ready, and the initial parameter setting will pop up right here. But again, user might change the number of layer and change the number of neuron there. So user prepare this list, integer list, for you to reset everything. So in reset, we need to check about this newly assigned the number of layers and layer number, and also probably update information about train ratio. So that should be done in reset. And after that, you just provide a public function, train epoch, train to end, which is similar to the meta-heuristic algorithm. So that's it. And then we need to interact with this chart in order to plot the current version. And also we need to deal with these graphics, right? Sorry, that's our job. So I kind of prepare a skeleton, a class skeleton for you in order to implement it correctly, because it's likely to do, because it's a little bit complicated. I mean, if you look into the data structure I suggest right here. So right now we have 3-dimensional array. Actually, it's in C#. It is not 3-dimensional array. It's a 1-dimensional array. It's a 1-dimensional array. The element is an array of array. Okay. This is the element of W. Okay, and within each element, again, that is array 2. So even though we regard it as a 3-dimensional array, but actually it's not 3-dimensional array. It's actually 1-dimensional array. But never mind, the structure-wise is clear for us. So basically, what I have suggested the name of the variable here is try to make you compare try to make the notation consistent with the notation that I use in my slide. So if you look into, well, you have better start from this example to catch up the idea or the implementation detail. So you see, input dimension is fixed. Right here, input. It is not a fully connected, it's not like the hidden neuron there, because in hidden layer neuron they have a weight connected to it, right? But initial, the first layer of neuron does not have any weight connected to it. I mean, in front of it. So in this case, I kind of use the 2-dimensional index for the neural layer. So x01, right? So that means 0th layer 1. If you use a special, then there are 2 hidden layers. So totally, the layer number should be 4. Should be 4 number, right? Start from 0, 1, 2, 3. So the last neuron should be the computational result of a training instance. Right? And then we will compare with the target value. We call it target value. But note that target value has a dimension start from 0, so D0, D10. So make sure this is the neuron X31. Where is the neuron X30? 30 is right here. Excuse me, 30 is right here. It is a dummy neuron there. So the whose value is not changeable. It's always equal 10. Because we treat the bias as a weight, as a normal weight, connecting with the dummy neuron in the previous layer, whose value is always equal 1. So that will be better for us to implement computation of vector and the matrix. So pay attention to the notation here. It's really L3. It's really easy to make a wrong implementation. Okay, so indexing wise is a little bit complicated, so make sure you write the right code. Okay, so you can think about that. Usually, almost data are two-dimensional. There are 2 indexes, right? So x11, that means layer 1, first neuron. 1, 2, layer 1, second neuron. There is a 0th neuron right here, 0th neuron, but the value is always equal 10. We are not going to calculate that. But dimension-wise, you need to allocate enough neuron for this layer. Even though the user tell you that the number of neuron here is 3, right? But the neuron actually you need to allocate memory is 4 because there is a dummy neuron there. So pay attention to the indexes of this data structure. Otherwise, it's really like to screw up your computation. And the weight has 3 indexes, right? So remember that weight is kind of belong to this neuron. So neuron X11, right? So we have a weight W110. The 0 means connecting to the previous neuron index. Previous neuron index is 0. 0 is 0, 0, 0, 1. So not connecting to the 0th neuron in the previous layer. So this weight, again, belongs to this neuron X11. And the third index is that this weight is connected to the first neuron or the previous layer. So similarly, this 2, 1, 1, 2. 2 is index pointed to the neuron in the IDs of the previous layer. So okay, and then you need to pay attention to that. So the computation is during the training is that we enter the input value or the data instance, then keep forward computation up to this end, and then we start from there. We need to compute the epsilon. Is a partial derivative of the error with respect to the net value, right? So epsilon 3, 1 is computed first. So again, epsilon is also associated with the neuron, right? So the dimension of epsilon, even though we just have we don't have any zeros epsilon, right? We have a neuron x30, but we don't have epsilon 30 because the neuron dummy is the dummy right here. So, but we still prefer that we allocate epsilon for maybe 3 instances, but we never use the epsilon 3130 there. So pay attention to the usage of your array, in your implementation. So once we compute epsilon 31, 32, and then we will compute epsilon 21. That depends on previous value of epsilon. So you need to pay attention to this computation detail. So once we forward up to this point, that's it. There should be no epsilon, especially in the zeros layer at all. So once we compute the epsilon 0, then we will compute the delta W. The delta W is in terms of the learning rate eta, right? The eta. And also, for example, if you are working on the, you're going to calculate the delta W321. Delta W321 is dependent on eta, and you see this is the weight connecting to X neuron X32, right? So we will need to use its value, epsilon value is 32, and also the original, the current value or neuron value X21 in order to determine the delta W of this weight. So once we compute the delta W31, we will use that update W32. So it's fair, right? The delta W value is depend on this epsilon and this neuron value. Okay, so similarly, how can we update this weight? This weight actually is a BIOS, right? So BIOS is similar because this weight is link the dummy neuron in the previous layer, right? X10, and also the current neuron X21. So we use epsilon 21 and the neuron value should be 1.0. Compute the delta W, that should be a delta of the BIOS value, W21, delta W210. And then we update this W210. So you need to carefully watch the implementation you done in your code, not to screw up with this index. It's very likely to screw up. So remember that. So you need to spend a little more time. But pay attention to that. We are not going to use all, even though we allocate memory for all value of epsilon and neuron value, but some of them we are unable to use. For example, we are not going to allocate memory for epsilon in the zeros layer, right? And also we will not have epsilon value for the dummy neuron there. Okay, but indexing wise, we should stick on the index, that means for each dimension there. Okay, so I have a suggestion data structure here. So probably the easiest way, right? Well, let me quickly set up a skeleton, the Visual Studio project. Then I will show you some graphics techniques you are going to need it. So to build up new project, make sure it's .NET Framework, C#. Okay. So probably let's click it. Make sure WinForm application, .NET Framework, not .NET. Okay, no, not .NET. And Location-wise, I switch my desktop, so you can easily pick it up. Make sure your dynamic framework is not higher than 4.8, because most of your computer does not have dynamic framework 4.8 installed. So if your notebook has 4.8, please select the dynamic framework lower than 4.8. Because usually our computer, our desktop does not have 4.8. So in that case, if I have your source code, I can download it. Otherwise, I cannot run your application. So normally, 4.6 is a stable version, but right now, I think you can stick on 4.7.2. So build up project name or 10. Fortunately, that should be the last assignment we have for this semester, right? Assignment 11. So add a solution keyword. Okay, so I have my desktop here. So probably I should copy I would like to copy maybe, well, never mind. You don't need to copy all of them, so I would like you to pick up iris, breast cancer, right? Copy that into my assignment, my solution folder. Let me put it there. You can wrap it up with a subfolder, you know, so I have it. You know. So back to our user interface. So I'm not going to check this for you. So for our MLP, we will prepare a class to contain all the required data in there. So I have suggested a template there for you. So if I kind of say my time, you can simply copy that. But again, the structure wise is not always correct. So you need to make your own modification. If you step up, if you so project add a class. Default name is class 1. Fine, even later I will change it. So I copied that from the instruction sheet and then paste it back. But since it's a PDF format, so probably some character that has been transformed, so probably you will have there, came out. So let me quickly check that. So I have a back propagation MLP. So every data has been prepared there. You can always start from scratch by yourself in order to learn how to design your data structure for the implementation. Okay, but so far, because this is a lab instruction, so I cannot take advantage of this existing code here. So back propagation MLP is a class name. Alright, so I do not have a string reader, right? String reader is class used to read textual file. So, well, let the Visual Studio help us. So using system.io is a required statement in order to let the compiler recognize this class. So we have a function skeleton here. So comment this one. Oops, made a mistake. This one. If somehow the indentation is gone, so you simply just cut and paste it. The editor will resume the correct indentation for you. So let's all cut it, paste it back. So the indentation will be reorganized. So this currently is working, right? All right, compile it to see if it is okay or not. Well, still a problem. This one is missing. You can also partially select a few lines, cut it, and pass it back. So the indentation will be resumed, which is stated for you. Okay, so let us take a look at the interface function. Fabric, right? Read it data set. Okay, so we prepare this function to read all the data here. Okay, input dimension. So the first lines I have prepared that for you, right? So user needed to have a string reader address. And I don't think the training ratio is required. So training ratio. No, we do not have training ratio here. So we cannot delete it. And then eventually you will set up a public property for the user to change it. So initially maybe 70% will be used for the training, 30% were left for the testing. So that is our intention there. So make sure you have a public property for it. So user might change that. I mean, once he before he quickly reset, right? So we will determine the training number by that time. So reading, what kind of data should we read? So as you can see, let us take a look at the file, the dataset file. So for example, breast cancer. Okay, so first line we have 4 numerical data, right? So each one will separate by comma, but probably might have some blank spaces, right? So in our separator, we try to declare that either a comma or a space will be regarded as the separator, comma or separator. So reading everything split it, we have expect 4 terms. So the first one is your input number. Input dimension, number of input, probably is name wise. If the name wise is not clear, maybe you can change it. Number of data. Number of data. Okay. Input dimension, target. Call it target, not output. Okay. Output is forward computation. After forward computation, we will have output value. And output value will be compared with target value. So the correct value we name it as the target value. So output value will be used for the forward computation from the input layer-wise up to the final layer, then we get output value. So output value will be compared with the target value. So input dimension, target dimension, input width, that's the first number I just mentioned about that. So then you need to look in for row start from 0, row up to number of data, right? Plus. So I'll ask you to do that by yourself. But once you know the input width, the number of data, what kind of data should, what kind of array should be instantiated? Let's take a look at it. The data-wise store the data set, right? Is right here. So as you can see, X will be memory allocated after reset, right? W2, epsilon 2. N is the number of neurons on layer. Okay, again, now it's specified by the user. So input dimension is confirmed number of data, number of training vector. Okay, this one will be determined later, right? In reset. So if the user changes 0.7 into 0.8, the number of training vector will be determined by that time. There. Original input is two-dimensional, right? You see, this is the original input. There is original target. So it's a two-dimensional array, flow. We use flow to read that in. Okay, and then so instance-wise, we read in the instant data, right? The first part will be the input, original input, and the real part will be original target. So fine, we know that. But we need to transform this original input into input. Input should be normalized, right? For each data field, we need to normalize the original input value into input value. So we need to calculate. We need to trace the maximum value for each field, for each input field. So for each input data field, we need to compute the maximum value, and so input minimum value too. So similarly, we have maximum value, target maximum, target minimum. Even though we know the maximum value should always 1, minimum value should always 0. But in order to make our new multi-layer precision general, so we were not going to expect the target value should be always 0 and 1. All right, so that is the purpose. So right here, once we know the number of data, then we need to, and also input dimension, right? And also target dimension, we should instantiate the memory right here. So what kind of memory should be instantiated? Original input mean, since it's a two-dimensional array, so we'll allocate the memory for that, for the input data, number of data, right? And how about the column? The column dimension should be the input dimension, right? We have input dimension obtained from the file, and also we have target dimension. So similarly, original targets, number of data, and also we have target dimension. All right. So similarly, your input should be exactly the same, right? So input and targets. But how about the input maximum? Input maximum, we need to compare the we need to trace. I mean, trace the maximum result. Input max. The dimension should what? The input dimension. Input dimension. So I'm not going to write all the code for you, okay? So similar. So in that case, so initially that means we have input maximum, right? So we were for input dimension, input max. We just want to set up one pass algorithm. So when we read in each instance, we trace, we update input max if the value is larger than the current input maximum value. So initially we need to set maximum value into flow. This is data flow minimum value. So output input min flow maximum value. Okay, I did not do the memory state instantiation for memory. So similarly, for the target, you need to update the target. So once we read in, right? So we are reading lines or a data instance. So we keep using this guy. S read line as split into items, right? So S is local variable, we keep reusing the items, So items, right? So start from column equal 0, column equal input dimension C++. So your original input arrow column C, right? Equal what? Equal float parser. We have another utility function provided by the data type, each data type parser string, strings items, C items. So I'm not going to write complete code. You need to think about the data structure right here. Because the data structure is not designed by you, so you need to spend a little more time really read all the information, read all the comment here in order to write correct code to set the value for them. Okay. And here we also need to check if original input RC is larger than the input max value of C, right? Anyway, we need to trace the to get the maximum value. Then in that case, the maximum value will be updated by this value. Else if original value is smaller than the minimum, right? Min. Input min equal original input RC. So anyway, so once we traverse, once you read all the line here, so you need to read, actually not read, set target parts here. Right, so you do the rest. So after we read in every data, I mean from the file up to the line, where we can close it. String reader SR. So probably it's outside the caller. The caller probably caller create a string reader. Caller will close it, but never mind. Up to this point, we can close the string reader. And then we need to transform to linear from original to input and target. Alright, so you need to, we simply use the maximum. We know each column has a maximum value, minimum value, right? So we will map the original input and make the mapped value to inputs, but also targets. So finally, during the training, we will use input value, which has been normalized. For each data field. And also target has also normalized, but actually, well, since right now the data set in general, you still need to do the normalization anyway. All right. So top input and target will be later on used by training. Okay, so up to this point, then we have another array linked to extension memory, right? XW, so that will be memory will be allocated in a reset function, and it should be provided by the user, right? So if n is an array or just one integer, that means the user just want one hidden layer, right? So this array should not be 0. So, but this n is not provided by the user. It will be used for us to cover all the neural layer. Okay, so n is not needed to be updated once user hit reset. So we have another index to help us to do the shuffling, to the input shuffling, and also to classify what kind of index should be the training data set and what index should be the testing data set there. Okay, so number of neural layer including the input layer. Okay, layer. So we have running rate initially 0.78 will be set up from the initial eta. Initially eta will be equal to initial rate. So from here. So property training ratio, okay, also depend on training ratio. So we have one derived data number of training vector, because right now it's kind of confusing. So number of training data. I change the name to make that consistent. Number of data, number of training data. All right, so you need to complete the read parts and do normalization right here. Okay. And okay, right here, compute a neural network. So in here, we need to determine the number of layers. So number, well, probably I will change that name. Total. Well, total number. Okay, never mind, stick on here. So you need to pay attention that hidden neural numbers is an array. So user will supply that. So you basically will pick up this array from the list box and then call this function. So this function will be called within your reset weight. Okay, so how can you do that? Because it's a popular function, so this function will be called by the caller, which is not means clear. For the use of your class. So we have better ask that for this interface one. So we're not going to set that as a popular function. So I do a little bit change right here. So we ask int reset weight and the initial condition. Okay, so we put everything right here. So we will ask for this array. It's a number of hidden neurons right here. So this one will be no longer public. It's a private function. It's turned out to be a helping function. So hidden neural number. So in front of it, we will call this function first. So we will call this function first. So once you use a hit reset button, this reset button will call this one a reset weight, and then user need to correct the user specify the architecture of the hidden neural net here, pass in as an array there. So we use that to compute our neural network. So let's go back quickly to this interface. So here, suppose later on, you carefully design your, well, okay, let me quickly do the job again. So we drag in manual strip. It's always automatically adapt to the top, and then tool strip. Because in the second layer, if you like to move the tool button in front of the menu button, it's very likely make that as the lower level. So tool menu is right here. Because they are colleague, right? They are colleague, they are brother each other. So depending on the order, added to the parent. So just try to you can figure out what's happened. So status strip and the split container in the middle. By default, you will duck the internet there. So we might provide a list box, right? So list box, I might call it LSB layers. Anyway, just a name. So later on, if user click on some other control, and finally it turned out to be, for example, 3, 4. As you can see, initially I just set it 4. So that means by default there are 2 hidden layers. The first hidden layer have 3 neuron space right there. So this list box is user interface. So, and then user will have a bottom layer reset. So let me quickly set a face text. Reset neural network. Alright, so after reset, then user can what? Run one iteration, right? So can train an aperture. So user interface wise, you need to do that by yourself. So initially the enableability is set to false. Enable property. Enabled is set to false, right? So similarly, we have run to end, train to end. Face text. And also we should have what? A property grid. But initially, you don't need to instantiate an object or multi-layer perceptron. I mean, so once you use it, here reset. This is reset. Usually, initially, you can instantiate an object for this multi-layer perceptron. So this should be no problem. So in your main form right here, so supposedly we have multi-layer back propagation multi-layer perceptron. Okay, I call it my MLP. So in your form, your constructor, we can initialize it. My new without any parameter, right? So we don't need to special anything. Then once we create it, we can have property grid 1. Select object equal my NLP. So when user click on this reset neural network, well, it just invoke my MLP that reset weight and the initial condition, right? So in that case, the main phone needed to pick up the value in order to construct an integer array. So I'm going to call it int neurons hidden. New, what about the dimension? list box, LSB, right? Layer, items, right? Count. It's a dynamic. It's a collection, so it's a count. You use count. Then for int I start from 0 up to hidden neurons numbers length is a fixed dimension array, so I plus. Okay, so we need to set hidden neurons as value. It's an integer, so int parser, right? List box layers, the items. It's a string, right? Parser, no. It's a list box object, so it's an object. So that's it's simple. We just invoke S2 string, so it turned out to be string pass into integer, so we get this array ready. So you pass that this local array, let the neural multilayer know that this is the array newly specified, newly updated by the user. So we can try that. So this function reset weights and set up initial condition, but before that, it's essentially reallocate memory for the weight right here. So back to this function, reset function. We call this configure function. So in configure function, you need to configure number layer. So right now, if you use a specify, well, the list has 3 integers. That means totally there should be 5 layers. And at the end, aggregates the newly set up total number of layers, right? So N0 is the first input output because right now we have target dimension ready there. So similarly, you need to copy all these values into this N array. N array will be used in forward and in training, right? All right, so after that, we will update number of training data equal what? Fraction, right? So we have probably user will change. Well, see. Let me see. In our propagation, we have 0. Train ratio. So quickly we encapsulate this private data. So we have a training ratio, user can set, user can get, but usually you need to set up a guarding condition. If value large than 0.5, which is reasonable, right? And value smaller than 0.95, only in this case, I will let you change the training ratio, which is reasonable. That means at least half of the data will be used for training. Okay, and at least 5% will be reserved for testing. I mean, that's total. This rule is total set up by you anyway. Training ratio. So once we in reset, we need to recalculate a number of training data. So that should be what? Number of, whoops. What is it? So in your reset right here, number of training data should be training ratio times number of data, right? And since it's integer, so we cast the number. So right now we know the limit of number, but before that, we needed to, we will again declare this index. We have an array right here. We have array, vector array. Well, I might rename it, called data index. Data, oops. Double click it, rename it, data index. Oops. Data indices. So how can we use this one to, so once you use a reset, right? Well, the dimension of this array is fixed once we read in the file. So here we read in the file, right? So number of data. Once we read in the number of data, we can arrogate memory right here. New int number of data. So we are not going to repeatedly because this array, the size is purely depend on the input file. Okay, so indices will be arrogate memory. I mean, if you use a keep reading different kind of data set, so we will update it. So once we have data set ready, so once the user hit reset, we kind of shuffle data indices. So this shuffle, this indices array is used to set up the sequence, the training order, and also set up the training data set and test data set. Okay, so let me draw a figure for you. So we kind of use these indices. This is the data set, right? The data set. So suppose this 0 up to 99, fine. So we have an index set up right here, index set up. So once we shuffle the indexes, for example, 5, 4, 41, 31, 50. Anyway, does that matter? If we shuffle these indexes, this is indices. Oh, excuse me. So this is original data. This is the indices. So we shuffle it. And then since we know the training ratio, right, 0.7, for example, times 100, so 70s. So number of training data. So this one, this kind of data, 50, 51, 80, 81, for example, probably is 3, 8, does not matter. So this part of index 5, 4, this one 5, 4, 41, this will be served as the training data. And then the real part, the index will be served as testing data. And also the initial sequence, I mean this index will be the order, training order, 5, 4 should be fitting, I mean during the epoch. And if user select one, well, in each epoch training, we will shuffle the training data. So make sure you just shuffle this part up to this part, because these parts are training data initially set up for the training, and this part will be reserved for testing. So pay attention to the usage of this indices array. If user saying that in each epoch training, we will reshuffle the order, the training order or the training data set. So we need to shuffle the index, just shuffle the index for this part only. Okay, so make sure you do the right thing. We are not going to shuffle all the data, because initially once the index has been initialized, has been shuffled, this part will be fixed, remain fixed, not repeatedly shuffled for training. Okay, so make sure you do the right implementation here. So we keep it. We are not going to change the organization of the original input and the target. Okay, so we just shuffle initial data. So we will invoke this function. We have this we was called what? Shuffle. Sorry, I cannot find it. Let me search it right here. Okay, call it randomized indices. Okay, my call it rename it shuffle. And then they have a int limit there. Okay, so if you want to shuffle indices array, right? So we have a limit shuffle index array. Okay, so so you need to do that. That means current from 0 up to limit -1. So you are not going to initialize the array right here, but in reset, in reset of the reset, well, we will for int I start from 0, I smaller than the number of data, I plus indices, okay, I exactly equal I. So initially we set up the order in the forward, and then we will invoke this shuffle array, shuffle index array, up to where? Well, totally, right? So initially it should be numbers of data. But during the training, you need to call this shuffle index array. But in that time, you will invoke this. Well, not here. Well, I'm showing the number of training data. So later on, I mean, it's not here, not used here. Okay, in here because it's initialized the training data set and testing data set. So we shuffle all the index in this array. But later on in training, I think in the perform impact training, if you use a setup option, you need to invoke this function, just shuffle the indexes array. So in that case, the training will be in that order. Okay, so here, so you need to carefully set up the dimension right here. Okay, so configure it. So n is ready, then you need to set up the w. So before w is setting up, I think the best way is that we try to allocate memory for what? For this x. X right here. Okay, read is done. Shuffle indices, reset, train epoch, reset, config, neural network. So config, right here. All right, so you know right now all the layer neural number has been stored in the n array, right? So x new. This kind of so-called jagged array, you need to instantiate the dimension, dimension by dimension. So first one is how many? And then the data type is a flow array. So how many layers right now? We have a layer numbers, right? We have layer number. So definitely that should be layer number. And as you know, as you pay attention to that, because the input dimension +1, why we +1? Because we have dummy neural data, right? In order to cover the bias as an ordinary weight. So we have a dimension increased there, a little bit there. So later you need to, once you need to special input vector, you need to be carefully about, you need to set up the right data correctly, because we have one additional neuron added for the it's a dummy neuron added for the bias. So you need to pay attention to this index. There should be one index. There should be one offset there. Okay. So x new these numbers, and then after that we need to loop through for int layer wise start from 0, layer small, then layer number, right? L plus x layer. How many neurons will be allocated? In L, right? So if you look into the structure, right now, how many layers we have? We have 2 hidden layers. We have 1 input, output. So total layer number 1, 2, 3, 4. So we need to instantiate memory for X neuron. So each neuron will have memory allocated, right? But how about epsilon? We do not have 0. But again, the first layer we don't need to set up epsilon 0 for it. But again, if you blindly allocate memory for epsilon, this is okay because there is no epsilon 01, epsilon 02 at all. But again, you still can make it that better. So doing that in this way. So similarly, how about W? Let's say mention that W will have an additional dimension, right? But that certain dimension is related to the previous layer. Okay. So W does not have the zeros index, right? So W starts from 1. So in that case, well, if layer is greater than 0, in that case, you can do something. Think about that. So here, W, L. So we do not have a W0 allocate memory for it, right? So before that, we need to new flow what? How many? The weight is an array, right? So similar layer, right? Layer number, right? So you need to, spend a little more time studying where is the right number that I specify. Okay, so take a look at this structure to set up as an example for you to check the correctness. I'm not going to say that currently I implement is totally correct. Okay, so you need to find out whether the specification by me is correct. So I'm just show you the procedure only. All right. So W0, okay, WL, new flow, and L. But again, that's an array. So we have epsilon, right? So epsilon is basically follow the neuron value. So layer number, it's 2-dimensional array. It's a similar epsilon L do not equal new flow and L. Okay, but how about W? So again, we need to set for int previous equal 0, previous equal what? Current is current L, right? So that should be current N L minus 1 P plus plus W L P go what? New flow. What should be very please? You need to think about this structure. Doing that by yourself. I'm not going to cover everything for you. and probably what I have input right here is wrong. So you do that by yourself. Get familiar with this multi-dimensional array. Alright, so once you done it correctly, and later on, if you bump into a more complicated array, you can deal with that easily. So make sure you do that by yourself. Okay, I'm not going to talk everything for you. Alright, so probably so you need to carefully instantiate the memory for those data. After that, I mean, computation-wise, it's so straightforward, right? So you see, in our user interface, we have reset neural network. So simply prepare this array, ask my MLP, reset everything. So it's almost done. So after that, we will invoke this one, train and epoch. Okay. So let me quickly compile it to see if there's any obvious error or not. Okay, right here. All right, so I comment this statement out, so let you complete it by yourself. So we need to read in a file, right? So we should prepare. But remember that in the very beginning, we have an object or multi-layer processor here for us. The initial we have rendering rate, we have training ratio ready for that. But user would like to modify the structure of this neural network and then quickly reset. After reset, well, we will draw the architectures of this neural network right here. And also needed to prepare the chart. Okay, so let me see if it is working. So we add a button, and also we have a file, and also an open command here. So if I double click this menu item, double click it, subscribe the event, it's called open 203 menu item click. So in that case, I can specify this button click event using the same functions. So open 203 menu. So because our MLP just take a string reader, right? So we need to prepare string reader, or probably we change it a little bit. We are not going to ask a user prepare a string reader for us. Probably we will ask user just give us a string file path. So we will do the instantiation of the string reader here. So we have string reader SR new file path. So in management, we create string reader here, and we ended it up right here, string reader close to make this functionality complete within this function. So we simply ask the user give me the file path. So back to our main form, what we needed to, you see, previously we instructed you can drag in open file dialog. It's a dialog. Open file dialog. You can drag in. So right now you have an object which can be used. Or otherwise, we can come here dynamically create. So the class name is open file dialog. BLG. We create instantiate the object, and then if BLG show dialog, we need to always check whether properly user cancel it, right? So dialog result is okay, make sure it is okay. We have a file path specified by the user. In that case, my MLP reading data set. So we simply pass DLG file name, which is actually a path for that file, to my MLP. So that works much better. So we instantiate and dialog, and then show up the dialog to interact with the user, get the file names, and pass that to the my name. So everything's there. So after that, So probably after that, we will let this button available. So you should need to always do the foolproof checking there. So user desktop. Okay. So we have five iris. Okay, iris fine. Where are we? Okay, because I have bug already, I did not extension memory for the input max, right? So literally, so that is your job to make sure every code is working well. So just let me test the skeleton or the current lab iris. Okay. I do not have input ready, so coming it out. So you should finish this coding iris. Alright, so it's done. Everything is done. Then we should reset. So user, let me set a breakpoint. Reset. Wait. Oh, okay. I have not mentioned about the wait yet. So just let us trace it. Reset and then come to here. Config. So you see, current hidden neuron specifier uses that user like to specialize two hidden layer, 3 and 4. So we then enter this function into here. So total number of layer right now is 4 layer. And excuse me, I did not set up the middle edge. So you need to do that. So remember that N1 up to you need to specify that. So in that case, this will be fair. I'm just doing this. Layer number is okay, but the one right here, it's okay. It should be 0. In that case, it should be 0 anyway. All right. So let me just make this part complete. For int, I start from 0. I want the hidden neuron numbers, the length. I plus. So new 1 plus I equal hidden neurons numbers I. Okay, that enter the number of neuron in. So I'm not going to cover the rest of it. So probably, okay, wait. So the job has one task we needed to compare: reset weight and the initial condition. So number date, training data set up. Shuffle away, and then we will initialize weight values. So as you can see, we will need help or randomizer. Right, so we already have a randomizer right here. It's ready for us to use. So loop through is for int row layer equals 0 layer, then smaller than weight, right? Dot length L plus for int. That should be the layer, right? So new one should be I equals 0, I smaller than weight layer. Length I plus for int j equals 0, then it's smaller than w l I next. J++. Is that okay? Yes. W, so right now we have layer, I's neurons, J's previous neuron equal IND randomizer. Well, it depends on what kind of upper and lower minima you are going to use. Suppose right now, initially it's like kind of conservative, so I set up randomizer that next double. So I get a value times times 2 minus 1.0. Since our weight defined in as a flow, so we need to cast that value as flow. So that will be the random value between minus 1.0 and 1.0. So initialize the weight. So once weight has been initialized, right? So the calculation of the neural network is ready there for you. So later on, user will click on a train and epoch. So we need to calculate the Roomy square L, right? So we kind of accumulate, start from the first one, right? Forward computing for all neuron value, with forward computing for all neuron value. Compute the epsilon value. In front, we should loop through each input data, each training, each training data, each data. Right? So go through each data. So for each training data, we need to compute all the neuron value and then compute the epsilon value, backward computing for epsilon value, and then update weight for all value, and update step size of okay. Update weight, and then train epoch, the end of the epoch, update step size, learning rate. So probably in the reset, we still need to do something. For example, eta, we call it eta, just directly use the name appear in the slide. Eta is equal initial eta. Why we have initial? Yeah, we need to have initial eta. Right? Initial eta. So initial eta is always fixed. We will use eta. So at the end, we will update what eta. Eta equal eta times learning rate. Well, the terminology is kind of confusing in the use. I mean, it's right, or probably in other resources. But make sure is that actually eta is the step size. We needed to reduce the step size at the end of each epoch in order to converge to we are not going to repeatedly change the weight. So the multiplication amount will be keep reducing. So means epoch by epoch. So we need to do that at our use. Okay, so that is the procedure for training. And then after that, we compute result. Well, this one probably we don't need to implement that because basically that is for usage. And so once you publish your neural network as an expert system, then you will take an input from the user and then predict the output for it. But we are not going to cover that. But in our code, we need to test the classification result. So this function will return confusing table out. So it's a table out. So you need to prepare this confusion table right here. So confusion table we dynamically allocate this memory because the memory wise is not large, so we can. Well, actually, this confusion table can be allocated memory once we read in the file. But here okay. To fulfill the suggestion, so I moved it out because the confusion table depends on the problem. So when we read in the problem, right, we know the input dimension, so we can instantiate here just one times confusion table. All right, confusion table is not special here, so we need to declare that as a data. It's a two-dimensional array. We don't know the exact dimension yet. Confusion table. So we also provide a public function here. Okay, they have a reference here. I'm sorry because that is an out. So we need to allocate memory right here. Okay, so we don't need that. So I might call it out confusing table. So at the end, we need to set out confusing table equal our confusing table. That's it. So you update the value of confusion table and then set that reference to this our confusing table back to the caller. So the caller will get well, actually that is a point, that is a reference to your confusing table because you put new value there, and also the caller will get this accuracy, the correctness value from its variable. So where should we call this test classification? Well, back to our caller right here, train an epoch, right? Train an epoch. So we will call my MLP train an epoch. That's it. So, and then you need to update the progress, the root mean square L, mean square L. Progress line. So remember that you have a line chart here. So in here, well, I will have another instruction probably next week where I show you how to draw a graph. So for today's lab, I just let you start in your application without graphics. So graphics is not so important at all, but we'll cover that. We'll cover that up in next week. So I add a split container. So we need another split container. Split container here. Orientation, we change that into horizontal. So in here, later on we will have a graphic draw in here, spec colors. So we need to set a spec color here. And in the upper parts, we will add a chart component that is related to the data. So you need to maintain this charting. Okay, so that should be the line chart so even we say you also need to clean up the point there. So the responsibility of the MLP should report current Loomis square L. Right? So Loomis square L should be reported by this multi-level position. So testing classification. Right? Alright, so main from round to end. So after round to end. So you call my MLP train. What is train? Oh, do we have a train to end? No, we don't have a train to end. So we just test classification train epoch. So never mind, we simply just add a public interface function. Train to end. Because stopping condition has been set up within this MRB, so we can train to end, and then up to an end user would like to do the testing classification. Test. Anyway, test fine. Just go. So button 3, train to end. After train to end, we might ask my MLP test classification. And then I will use out get this array. So here I have a local int. Just since it's a two-dimensional array, so it's just a reference to this confusion table. So this function will return this confusion table to me, so I can display it. I can check out the value and then use the string to display it on my user interface. And also I get a flow value, right? The correct image. So train to end, and then ask my MLP test data, report the confusion table back to me, and I also get the correct image. So then display. So just drag some visual display control. So as you can see, it's in my demo application. Which is similar to here. Okay, so this is the list, right? And once we read in a file, so provision ready, and then user can change the parameters. After that, after reset, this part will be covered by I think in the next week. I will show you how to draw geometric geometric figures on panel, but you need to create this chart by yourself to display the progress of the Rubik square L. So train epoch. You see, display Rubik square, current Rubik square. So definitely my MLP should report this as a property for you, right? And once we get a property, we need to access the current weight. So later on, we will set up properties of my MLP so that our mainform can access the current weight value and display it right here. And also not just current weight, also the current new norm value to display the value here. So once user click train to the end, finish the training and also do the testing. So we will get this confusion matrix, confusion table, show up the information right here. And also we have corrected this value, returned it. So we can get it displayed right here. So pretty much that will be the requirement for this assignment. And if you add your GA, add your PSO here, extra credit will be given, right? So in fact, I mean, intrinsically, training on neural network actually is an optimization problem. So we can always use different kind of meta heuristic algorithm to do the training for the neural network. So, all right, I'd like to end it up right here. Is there any question about this assignment? So as you can see, this assignment is involve different kind of techniques. So you need to spend a little more time studying about the formulation. We did not implement this MLP as an object-oriented structure, so we cannot lump sum all the computation once together in order to deal with multi-level. So it doesn't matter. It doesn't matter how many hidden neural has been specified by the user, because the computation is so straightforward, and the training will just one layer back, layer by layer, transform it back, and then later on we will update the weight according to it. So computation-wise, it's so straightforward. There is no any requirement to do so probably prepare a layer class, another layer class we did not do that. But actually, if you like, you can implement that in that way. But efficiency-wise, it's not good at all. So right here, we study the formulation carefully and then implement it, and it should work anyway. Okay, is there any other question about the current instruction? So definitely the due date should be more than 1 week. So in the next week, I will continue the lab instruction to show you how to draw. But the most important part has been instructed in this lab. So you need to step into this assignment as soon as possible in order to catch up everything, or probably notice that is there any part missing in my instruction. So later on, I can edit it up in the next week. Okay. All right. So that will be all for today. So if you have any other question, please email me or just come to my office. Okay. So that will be all for today. Okay. Good luck.